Good morning or good afternoon. My talk today is about an innovative 3D joint that was developed to enable steel modular construction with a reusable system. The contents of my talk will first, after this short introduction, will briefly present the Inno 3D joint system, then the technical developments that were undertaken in order to develop this joint and prove its performance, and finally our contributions for design specifications and sustainability assessment. Finally, I'll wrap up with some short conclusions. What were the drivers for the development of this project? First, we wanted to improve the efficiency of cold form structures as primary structures, both for residential and office buildings. And we thought that it would be efficient to take advantage of tubular columns. Of course, having in mind that we wanted to enable reuse, which is a crucial point nowadays, and of course fast erection. So basically, we wanted to develop a system that would extend the current range of application. This means more stories, higher buildings, and larger free spans. This project was funded by European Union, the RFCS fund for coal and steel, and within a project called Inno 3D Joints that combined a pan-European partnership of several institutions around Europe that was led by the University of Coimbra. Let me now make a brief description of the Inno 3D Joints system. The system is illustrated in the short video that shows the ease of installation and dismantling of a truss that slides into a socket welded to the column. And the beauty of the system is that you can have one beam, two beams, four beams, therefore making it a true three-dimensional system that allows for a 3D space grid with flexibility in the layout. The key ingredients of the system, and therefore enhancing its modularity, are for cold form or tubular steel trusses, tubular columns, a CLT floor that was chosen in view of its environmental performance and its lightness and ease of installation and the good finish, and finally infill wall panels that can or not exist depending on whether we want an open or a closed span. But the key thing about the system is, of course, the development of this plug-and-play joint. And here you can see the key ingredients of such a connection. First, on the column side, you have what we call a socket, and on the truss side, we have what we call a plug, which slots inside the socket, therefore allowing to transfer load both at the level of the top cord and the bottom cord, as you can see here. So to transfer shear and to transfer a global bending moment. You can see here as a final illustration of the system a view from the bottom floor, and here a full size model building that we tested in our lab. So what were the technical developments that were necessary to enable the development of this solution? The main challenge of this project was, of course, to develop the characterization of this hybrid joint. Combined with that, we had to assess the structural performance of the system to ensure that we could have appropriate performance as a moment resisting structure. We had to deal with the execution challenges and the reusability issues. And of course, we had to provide design tools that would ease the use of the system combined with the development of normative guidance. The strategy to study the behavior of this joint was to break it down into its individual components and then to study each of them individually. In the video, you can see the experimental test and the corresponding numerical simulation showing good agreement and allowing the development of a proper design model. A large parametric study was carried out for the socket in tension or compression, comprising 33 experimental tests of sockets with different geometries. We're talking about varying thickness, varying depth, or varying the presence of stiffness. The same was done for the other side, the bracket, the clipping T-stub in tension and in compression that you can see here, again with the same strategy. Extensive tests and corresponding numerical simulations, and the results are illustrative results are shown here, where you can see good agreement between the experimental and the numerical results. So second step was to test the full joint. In here you can see several combinations that allowed you to have a range that goes from full strength configuration to equal strength and partial strength. Again, to be able to provide flexibility for the system and to choose the best options. This video shows the experimental test of a complete joint and the corresponding numerical simulation, and good agreement is noted between both. In this slide, we put together the full set of experimental results, and it is possible to control the behavior of the joint, ranging from more rigid to more flexible joint, depending on the geometries, the detailed geometries that are chosen. The two next steps correspond to the testing of a complete subframe, and we tested three possibilities. First, a subframe with two types of sockets, and then a subframe with an infill panel. In a total of 9 tests, and you can see here the results. And then finally, we tested a full-scale 2-story building that was tested in our lab, loaded at with vertical gravity loading and horizontal loading with these two hydraulic jacks, as you can see in the picture. The gravity loading was implemented with sandbags and with 7 configurations. So we started from the frame, the structure with infill panels on both sides, and then progressively we took each subpanel one at a time to test up to serviceability until the bare steel frame without infill panels. And this is just a picture of the structure before the full-scale testing, already without any infill panels. The dead load was about 50 tons, and globally we can say that this demonstration proved that the system was good to go. The final step in this development was the preparation of design rules for the developed connection and to prove that this connection could enable a reusable structure that would present significant advantage from an environmental point of view and also from an economic point of view. So starting with the first aspect, design rules, of course, it is important that we try to frame all our developments in the scope of, in our case, the Eurocodes. And so thinking about a future version of Eurocode 3 Part 1.8, this clearly falls into a situation where we want to design, develop rules for hybrid joints. And by hybrid joints, I mean joints that combine open sections with close tubular sections, which is something that is not present at the moment in Eurocode 3 Part 1.8. So this is our proposal, is of course to maintain the current approach of the Eurocode, include the specific chapter for hybrid joints, and enlarge naturally the list of basic components with a specific focus in this case of basic components for tubular joints. So and of course the detailed rules for this type of connection, which we would call it an Annex F, moment resisting truss to tubular column joint configurations. I will briefly just highlight the key aspects that are specific to this joint, and the key aspect here is the equivalent cross-section component model for RHS tubular members. Because in this case, even if you're connecting only to one side of the tube, you are really getting a three-dimensional effect, because all the other faces will also be deformed, and you have to account for that in your connection. And of course, this happens at two levels, the level of the top chord and the level of the bottom chord. And this was the object of the draft specification for this in our delivered in our project documentation. That then, of course, requires the specific design rules for each component. I'm just highlighting one here, the rectangle hollow section facing out of plane bending, because in a general configuration or in a general situation, you will have these two cases. You have two plates that will be welded to the column face either horizontally or vertically. In this case, vertically. And you need to be able to assess not only the resistance of this case, but also the stiffness. And this was also developed in the project by our partners from CTI-CM. Final note on sustainability. Of course, the advantage of reusing here means that there is a large advantage and large gains on this, the possibility to have a structure that can be reused. And with this, I conclude. Thank you very much.